Are we recording? Oh. Hello everyone, welcome to International Trade. I'm very excited today to start a new model and a whole new theory of trade with the new trade theories. So this is going to be a two-part lecture where we're going to start our analysis of the so-called new trade theory. Okay, we're going to basically going to really change the pace and the broad characteristics of models from now on. And we're going to distinguish between, the sort of old school models, like the Ricardian model, the Axial model, but also the offshoring models that we studied, despite some of them being fairly recent. And this is going to be motivated by a series of failures of the previous models. So now I'm going to show you some evidence that points to some limitations, to use a euphemism, for the old school models of trade. So first of all, recall that the main reason why countries trade in the Ricardian and Axial model is that countries are different. Different how? Well, in the Ricardian model, countries differ in terms of their technology. In the Axial model, countries differ in terms of their endowments of the factors of production. Well, let's look at how this happens in the data. Recall in the very first lecture, we looked at the main Danish trading partners. Here I'm just reporting that table. And notice here that we have some countries, I highlighted them in red. So just look at these countries. What do they have in common? Well, they're all high per capita income countries. Right? Some countries are relatively richer than others, say Norway, right? Or even the US, when you compare it to, say, Italy, okay? But they certainly have much higher income than China and Poland. So are these countries differ from Denmark? Well, do they have different technology? Maybe, but say pick Sweden. Okay, is Sweden different from Denmark in terms of factor endowments and in terms of technology? Well, perhaps, right? Perhaps there are some differences, but when we look at the aggregate implications on wages or per capita income, since the per capita income in Sweden and Denmark is relatively similar, right? What that means is that neither of the two countries has really an absolute advantage in anything, right? They both have the same average productivity. And if we look that through the lenses of the Axial model, that means that the capital intensity in the two countries, how much capital per labor there is, if you want, you can also think about it in terms of capital abundance, is pretty much the same. Workers on average have the same number of machines, the same technologies, hence the per capita income in the two countries is the same. Okay. Now, how is it possible that if Denmark is so similar to Sweden, the two countries are still trading? That's a big question, okay? And of course, you can think, well, perhaps Sweden has relatively better, on average, the technology of Sweden is the same as Denmark, but in Denmark, we have a relatively better technology in the production of energy producing plants, and Sweden has a relatively better technology in producing cars. That is why there is this trade. Perhaps we are relatively more abundant in cows, they're relatively more abundant in wood, and that's why we specialize in dairy and they specialize in furniture products. Fair enough. That's a fair objections. But so let's see what these countries actually trade in. Now, in the Ricardian and Axial model, very important result was that there is sort of when you export a good, you never import it. Okay, so if you're in the Ricardian model, you have a comparative advantage in good one, you're gonna export good one, but never gonna import good one. Same thing in Axial. Countries specialize in the production of their comparative advantage good, they export that good, and import the other one. So let's see if this is actually true in the data. Okay. To do that, we're going to develop a measure of so-called intra-industry trade, trade that occurs within an industry. In other words, we want to account for how much a country exports and imports for a given industry. So the way to measure this is with this index, which is computed as the minimum between imports and exports divided by the average between imports and exports. In the Ricardian and actually model, what is the value of this intra-industry trade? Well, it's 0. Why is that? Well, because within an industry, say, computers, what is the minimum between your imports and exports? Well, if you have a comparative advantage in computers, you export computers, but not import them. So your minimum between imports and exports is going to be 0. Same thing if you don't have a comparative advantage in computers. In the case, your exports are 0, and so the numerator is always 0 in the Ricardian and actually model. How does this look like in the data? Not 0. Here I'm highlighting that this is the average intra-industry trade for Denmark, in a series of other countries across years. And you see that this is 61%. Okay, so this is much larger than 0. If this value on average was, 5%, we can think that there is some weird things going on. But here, if there's like 60%, and if the ratio between your minimum between imports and export and the average import and export is 60%, there is some serious intra-industry trade going on. You're exporting a lot of computers, and you're also importing a lot of computers. What is going on? How can we make sense of this? Well, let's think a little deeper of what type of products are characterized by a higher intra-industry trade. Well, to see that, let's look at the index of intra-industry trade, in this case for the US, across different product categories. For instance, here we have vaccines, which I guess we're all thinking about them these days. For the US, you see that the value of imports is about 2 billions and the value of exports is 2.7 billions. This is equivalent to an index of intra-industry trade of 85%. So a lot of intra-industry trade. Whiskey, same thing. Could also talk about golf clubs, but I don't know much. I know even less about golf clubs than I know about vaccines and whiskey. Or if we look at instead at the bottom of this table, what do we have? We have telephones. I have value of intra-industry trade of 17%. Imagine here old school telephones. And here you have men's shorts. Index of intra-industry trade of 3. So what is the main difference between vaccines, whiskey, and men's shorts? Or even apples? Okay, so index of intra-industry trade of 31%. Well, the key difference is that while there's really, just one type of men's shorts, there are several different types of vaccines. I mean, we're seeing it these days, right? There's not one vaccine for COVID. There's AstraZeneca, there's Moderna, there's Pfizer, there's the Sputnik, and hopefully there will be way more in the future. But so, same thing for whiskey, right? There's different types of whiskey, okay? I guess Scottish whiskey or Kentucky whiskey or other things like that. Okay, so basically what is happening here is that there are some goods in which there is a lot of intra-industry trade because there is a lot of product variety within that sector. In other words, vaccine is not a homogeneous good like the goods that we implicitly consider in the Ricardian and actually model. Vaccines is a differentiated good for which there are a lot of varieties. And therefore, you can imagine, where we're going with this is that we're going to have a model in which countries produce different varieties of vaccines, and countries trade because they also want to consume the variety produced by the other countries. In contrast, men's shorts is pretty much a homogeneous good. Right? There's not much product variety there, and as a result, the standard models of Ricardian and actual comparative advantage works very well. Okay, now we're also going to make two different assumptions from actual and Ricardo. The first one is going to be, we're going to abandon the idea of constant returns to scale. And this is clearly motivated by this type of goods, right? We've seen in these days with the vaccines, there's really not a constant returns to scale production. Because, well, first of all, there is all the research and development that goes at the beginning. And second, we're seeing there's some fixed cost associated with opening new plant to scale up production. Okay. Furthermore, we're gonna start, and this is perhaps the main difference with respect to the old school models. In these new trade theories, what we're gonna have is gonna be a focus on firms. In the Ricardian and actually model, we kept saying that countries trade, countries exports, and they do, and it's very simple and easy to think in these terms. But obviously, in reality, there's no such thing. Countries do not trade. It is the firms within the country that exports and import. And therefore, what we're going to start doing is take that seriously and examine more carefully the problem of firms. We're basically going to see two models, both due to the great Paul Krugman, who won the Nobel Prize in 2008 because of these papers and another paper very related to this that he worked on in the 90s. Paul Krugman is a great trade economist, has also been working, especially in recent years, in macroeconomics. He is very famous not only in the economics profession, but also, I have to say, in the public debate, because he was never afraid to voice his opinion about things such as the Bush administration, the war in Iraq, and the rising income inequality in the US, even before it was cool to think about income inequality in the US. And he has a blog and a column on the New York Times, and is always very, it's good fun to read him. So he wrote two papers that we're going to study today and in the next video lecture. The first one is the Krugman 79 model. And for that, we're going to look at the main assumptions, look at the autarky case, and then move to trade. And then we're going to do the same thing for Krugman 1980. But the way we're going to do it is you're going to see that basically Krugman 1980 is a particular case of Krugman 79. And we can call these models the models of trade with monopolistic competition, or also with the monopolistic competition and increasing returns to scale. So let's begin with the first of the two models. In the Krugman 79 model, if we look at the closed economy, there are going to be n product varieties. You can think of this n as being the number of firms. So if we think of vaccines, this would be Moderna, AstraZeneca, Pfizer, and so on. This was beers, this would be, Carlsberg, Tuborg, Heineken, and so on. An important feature of this n is that it is endogenously determined. And in particular, a crucial objective of our analysis is going to be to study how trade affects this number of varieties. Now, consumers are going to have this additively separable utility function. Basically, your utility is the summation across all of the varieties I, from 1 to n, of your consumption Ci, which is evaluated by this function V. Okay, this V could be a lot of different things. And you're going to see in the homework and perhaps in the problems that we do together on Wednesday, different formulations for this V. Now, V prime is positive. The more you consume of a variety, the better off you are. And V double prime is negative, so there is sort of diminishing returns to consumption in one variety. These preferences, we're also going to assume that they have a love for variety. What does that mean, love for variety? Well, let's see. What does it mean to have a utility function that exhibits love for variety? So the idea is that suppose that there are n product varieties. Suppose that they all sell for the same price P. And finally, let W be your income. So the question that you need to answer here is, well, would you rather spend all of your money on one product or rather share the income equally across the different varieties? Well, we have love for variety if you prefer to spread your income across the different varieties relative to the case in which you spend all of your income on one good only. So if you split your income across all of the varieties, what is your utility? Well, your utility is, was the summation across all varieties indexed by I from 1 to capital N of V of Ci. If you divide income equally across these varieties, what do you get? Well, the consumption Ci of each variety is simply going to be your income split across all of the varieties given their price. Okay, so that is the amount of consumption that you have for each variety. You evaluate it as V, and then you multiply this. This is the same for all the varieties, and so what you have is capital N that multiplies that term. Okay, so this is one option. What is the other option? The other option is to spend all of your money on one variety only. Well, in this case, what do you get? Well, you get that all of your income goes into one variety, and so you have is V of C of the single variety that you consume. The quantity of which you consume is W, your income divided by its price. All of your income goes into one variety. So love for variety means that the variety you get from consuming all the varieties and spreading your income across this, which is this part here, is larger than spending all of your income on one variety only. So let's write it out. N of V W over NP, which is the utility that you get when you spread your income across the varieties, is actually larger than V of W over P, which is the utility that you get when you consume only one variety. Now, is this love for variety, is this real? Is this a true assumption? Is this an assumption that is reasonable? Well, you can think about it in two ways. One way is the introspective way. So, think for yourself. pick different product groups, you know, beer, food, clothes, and so on and so forth. And imagine, would you rather spend all of your income on one variety only, or would you prefer to share your income across more than one variety? If it's the latter, then you have a love for variety. Another way to think about it is to think that indeed, perhaps consumers do not have love for variety individually. Each consumer has a variety that they like the best. You know, I like espresso, you like latte, or I like, I don't know, Carlsberg, you like Tuborg, right? When we aggregate the resulting demand from consumers that have different preferences, but the representative consumers that represents them has love for variety. So that concludes our analysis for the consumers. And now we can look at firms. Okay, so we're going to have monopolistic competition. So this is, you know, we have a large number of product varieties. Each firm has a monopoly power over its own variety, in the sense that nobody else can produce that particular variety. And so it has some monopoly power over the price of that variety. It does not have to charge the same price of all the other firms, because if it does that, it's not gonna, you know, if it increases its price relative to all other firms, it's not gonna lose all of the customers, right? Because the products are differentiated and some consumers will still like the product regardless of the higher price. Or we call this monopolistic competition because there's so many product varieties, so many firms, that they're competing with one another. So there is a limit to the price, the market power that these firms have. Now, each firm is going to be indexed by I, by the variety that it produces, and produces one variety. Obviously, there are models these days as with multi-product firms, but we're going to actually talk about it in the very last lecture of this course. So each firm supplies a variety with quantity yi, and you know, you can think that yi is the product between ci, the consumption of one individual, times the number of individuals, which will be L. Labor. Labor is paid a wage W, and there is a labor requirement per firm. Li, so the number of workers for firm I, equals to alpha plus beta times yi. So let's start with beta. What is beta? Beta is the variable labor requirement. How many workers you need to produce one unit of output. So that the total number of workers you need to produce y unit of output is y times beta. And then we have alpha, which is a fixed labor requirement. You need this many, you need alpha workers, whether you produce 0 units of output or if you produce 1 million of them. Okay, so alpha represents a fixed cost. You can think of this fixed cost in very general terms, okay, because you can think of this as an R&D cost. You can think of this as a fixed cost of production, you know, the setting up of a factory, and so on and so forth. Okay, so to solve this model, we're gonna first look at the consumer problem. Right? So we're gonna solve for the indirect demand of consumers, derive the demand elasticity that we will use in the firm's problem. And then we're gonna close the model, imposing the free entry condition to figure out how much production there is of each variety, how much consumption, and how many varieties there are. So let's begin. Let's start with the consumer problem. The problem of a consumer is to maximize its utility which equals the summation from I equals 1 to capital N of V CI subject to the budget constraint. Budget constraint, which equals the summation over all the product variety I from 1 to N of PI times CI, so the price times the quantity consumed for the good, is going to be less or equal to the income, which is W. So to solve the problem, let's set up the Lagrangian. So we have summation I equals 1 to capital N of V CI plus lambda, which is the Lagrangian multiplier, wage minus the summation across all product varieties of the price times the quantity. So the first order condition with respect to CI equals, and we have V prime of CI, which equals lambda PI. So we can write this as an inverse demand function if you prefer. That is, the price PI equals V prime of CI divided by lambda, which is again the Lagrangian multiplier, and from your micro course you also know that it's the marginal utility of income. So how much you value an additional kroner of income. Now, what we want to do now is derive the demand elasticity. So the price elasticity of demand, which we're going to denote by eta of CI, is going to be defined as minus the derivative of CI with respect to PI times PI over CI. Okay? Now, if we look back at the demand function, let's first of all, let me write number 1 next to it so that if we need to reference it, we will be able to do so. So if we want to derive the demand elasticity perceived by a firm, we're going to need this eta for the solution to the firm's problem later on. What we need to do is to take the derivative of this demand function. Now we take the total derivative, and then we can figure out what is the demand elasticity. Now, a crucial assumption of the Krugman model is assumption of monopolistic competition. And in monopolistic competition, the idea is that firms are so small that they do not affect the lambda. They do not affect the marginal utility of income. In other words, they do not affect, in general, any market aggregates that appear in the inverse demand function. So let me write this explicitly, because this is saying that under monopolistic competition, okay, and so the idea is that when a firm changes its price, it's going to affect the quantity consumed, but that's not going to affect, or at least the firm is not going to internalize the effect that that decision has on the market aggregate, because the firm is so small that takes the market aggregates as given. So this means that to derive eta, we need to take the total derivative of 1 holding lambda constant. Okay, so let's do that. Let's take the total derivative of the inverse demand function, the total derivative holding lambda constant. So what do we get? Well, we get that dpi equals v double prime ci times d of ci divided by lambda. Okay, excellent. Now recall that v double prime is a negative, right? So this makes sense, and there would be a negative sign there somewhere. Okay, so now what we want to do is we want to substitute the inverse demand function into this expression. Let's call it 2. In other words, what we want to do is to substitute the lambda. And so what does this give us? Well, this gives us that so dpi divided by pi equals v double prime of ci times dci divided by v prime of ci. Okay, so if we the last step that we need is to multiply and divide both sides of the right hand side by ci, and then we can obtain our demand elasticity eta. So recall that we define it as a negative sign times dci in dpi times pi over ci, which equals minus v prime of ci over v double prime of ci times ci. Okay, and recall v double prime is negative, so the fact that we have a negative sign in front of it suggests that the eta is positive. Okay. Now, what can we make of these etas? Well, we're going to make a crucial assumption here. So, assumption of Krugman, 1979, the first paper of the two, which is actually written in the paper as he makes this assumption without apology. He assumes that this demand elasticity eta is declining in Ci. Okay, so it's basically saying that the more a good is consumed, the less elastic the demand for that good is. And we're going to see later on that this has an important implication for the markups of firms, and this is perhaps, and that is perhaps the most appropriate way to rationalize this assumption, to understand this assumption. But notice that this assumption that eta prime is less than 0 is not that crazy, because for instance, the linear demand that I presume you've seen in your past belongs to this class of preferences with declining demand elasticity. Let me briefly rewrite here a few variables. First, we have yi equals L times Ci is the total output of firm I. And then we have the beta is the marginal, the variable, like the marginal labor requirement. And alpha is the fixed labor requirement. Okay, so the objective of the firm, as always, is to maximize profits. What are the profits equal to? Well, the profits of a firm by I are going to be equal to the total revenues, so the total output of firm I, yi, times the price, pi, minus, well, we have the variable costs, right? So we have W times beta, that's W is the wage, beta is the number of units of labor you need for each unit of output, times yi. And then we have the fixed labor requirement, so we have W alpha. Alpha is the number of workers you need for the fixed costs, and W is the wage. Now we're going to rewrite this as substituting for total output, so that we have LCI of PI, which, recall, is also a function of CI. Let me go back up. Recall that our pricing equation is a function of CI, and that's the case all the time. Then we have minus L CI W beta minus W alpha. Okay? So let's take the derivative of the profits with respect to the consumption CI. And so the first order condition FOC equals, well, we're going to have is L times PI, right, of CI. Okay, let me write it explicitly fully, plus LCI D of PI in CI, which is equal to LW beta. See here the L disappears because it cancels out. And then what we can do is actually factor out the price out of the left-hand side. So what we have is that PI, I'm going to stop writing the argument CI, PI multiplies 1 plus dPI over dCI times CI over PI, closing the square brackets, equals W beta. So what about now? What can we do now? Well, here we have the derivative of prices with respect to consumption times CI over PI. Well, that looks a lot like our demand elasticity eta, doesn't it? And so we can actually write that first order condition becomes PI 1 minus 1 over eta of CI equals W beta. And so we have our pricing equation. Pricing equation or pricing rule is going to be that, let me write it in red, PI equals W beta times eta CI over eta CI minus 1. So what we have here is the marginal cost, W beta, that is the marginal cost of producing 1 unit of output, this is MC, and eta over eta minus 1 is the markup Okay, so with monopolistic competition, we have that firms charge markups over the marginal cost. This is a huge departure from all the models that we've seen in the past, right? Now the question is, are these markups increasing or decreasing in output CI? So let's see. Let's take the derivative of that. We have the derivative of eta CI divided by eta CI minus 1 dCi. Well, that equals, so derivative of the numerator, so eta prime, eta, I'll forget about the argument, eta minus 1. Then we have minus derivative of the denominator, eta prime, times eta. And this is divided by eta minus 1 squared. So what do we get? We get, now let me write it fully, just because I'm enjoying this iPad writing. Though I'd much rather get my hands covered in chalk and do this at the blackboard. At least I get to walk instead of just sitting down. Okay, so these two terms, eta prime times eta, cancel out. And so what we get is minus eta prime of CI divided by eta CI minus 1. So is this term positive or negative? Well, let's look back at the assumption before. Right? We have assumed that eta prime is less than 0. And therefore, if eta prime is less than 0 and you have a minus sign before eta prime, what you get is that this term here is positive. Okay, so markups increase in CI. So if CI increases, markups go up. Oh, this is indeed what we observe in the data by and large, because what we see is that the largest firms that produce the most, actually charge the highest markups. Okay, you can think of an alternative framework in which you have, you know, like these boutique shops that charge higher markups relative to, say, some big retailer, but then that's more of a anecdote or less empirically relevant. Okay, but so this should give you some intuition as to why we assume that eta prime is less than 0. Basically, what we have in this model, that firms that produce more charge higher markups. And that is because by producing more, the demand elasticity they face declines. Consumers are less sensitive to the price of products that they purchase a lot, and therefore, firms can charge higher markups. Excellent. Now, a crucial thing about the firm problem, if we go back and look at it, if you look at the pricing equation, we have that the price PI, right, of a firm I depends on the marginal cost, which is the same for all firms, and then depends on the markup, which is a function of CI, right? But CI is also a function of the price, right? Because, I mean, we have the demand equation that we showed before in 1, right? So PI and CI are related by a one-to-one mapping, and therefore this pricing equation really applies for all firms. In other words, what we have in this model is that firms are identical. So this is a model of homogeneous firms. Which means that Pi equals P for all I, and the same thing is also true for Ci. Okay? But so what we have here is indeed a first equilibrium condition. It's the pricing equation, which we're going to write it as P over W equals eta C divided by eta C minus 1 times beta. Okay, and we bring the W to the left-hand side just for convenience. I will talk more about that later. Okay, so this equation is a first equilibrium condition, and we're going to call it PP. And since the markups are increasing in C, if you plot this condition on a P over W C plane, you get an increasing function. So if we have C on the horizontal axis and P over W on the vertical one, what we have here is an increasing function. Okay? So this is saying that the more you consume of each variety, the more C increases, the higher the price over the wage, and because of the higher markup. Excellent. So now let's move on to the other equilibrium condition, which is the free entry condition or the zero profit condition. So all firms can enter by entering, well, you know it from microeconomics, when firms enter, the residual demand for each surviving firms, shift to the left and becomes flatter, so profits decline. And what happens is that more and more firms enter until the profits are driven down to zero. So our objective now is to write this zero profit condition, this free entry condition, and we're going to write it in a way that we can represent on a P over W C plane. So recall that our profits are, for any firm, right, because it's the same for all firms, are equal to the output times the price minus well, the variable cost, wage times beta times y, minus the fixed cost. We want to write this free entry condition such that we have a relationship between the price over the wage, P over W, and the consumption per variety C. So to achieve that result, what we're going to do is, well, first of all, we're going to set this profit to zero, because that's what the free entry condition states. And then we're going to do is we're going to keep the price on the left-hand side and set it equal to the whatever is left. And we have the wage, beta, the y cancel out, plus alpha wage over output. And therefore, if we divide both sides by the wage, we have P over W equals beta plus alpha over Y. And since we care about CI and not total output Y, what we have is P over W equals beta plus alpha over LC. Now let's think a little bit about this. What is this saying? Well, here we have the price over the wage equals to the variable cost beta plus the fixed cost over the total number of units of output produced. So what this right-hand side is actually the average cost. It's total cost divided by output. Okay? And so this is an interesting parallel, right? Because this equilibrium condition, which we're going to call ZZ, or zero profit, is basically saying that the price equals the average cost. And the PP condition is saying that the price equals a markup times the marginal cost. Okay? Now, what does this relationship look like on the plane that we drew before? Well, we have the C P over W. Well, in this case, P over W is declining in C. So if we combine ZZ with the PP curve that we drew before, we find our equilibrium. Okay? So the intersection between these two curves identifies the equilibrium price level, P over W, and the individual consumption per variety, C. Okay, so question, why are we using P over W instead of just P? Well, you know from Walras' law that if you, if n minus 1 markets are in equilibrium, the nth market is in equilibrium. And for such reason, you can only express prices relative to something. Right? So in this case, what we're doing, we're expressing the prices of all varieties as a function of the wage. We could normalize the wage to 1. We will do that in the future in another model. Here we leave it explicit because that's what Krugman does. Also notice that P over W is an inverse measure of welfare because P over W is the inverse of the real wage, the number of units of output that you can purchase. Okay, so are we good? Are we done now? Have we found the equilibrium? Well, there's something missing. What's missing? Well, we need to find the number of varieties. All right, that's the new part of this model, that the number of varieties is actually endogenous. Okay, so we have to determine it. But what is the number of varieties equal to? How can we find it? Well, there's two ways, right? Because it suffices to look at different various possible equilibrium conditions, market clearing of various sorts. That's what we're going to do in part. We're going to look at the full employment condition, right? Like we did in the Krugman model, in the Ricardian model, the Exorlin model. Full employment condition. So let's see. How many workers does a firm need? Well, a firm is going to employ alpha workers for the fixed cost plus beta workers for each unit of output Y. Okay, so this is the labor requirements per firm. There are n firms, so this is the total labor requirements. Well, this must be equal to the total supply of labor L. So that if we rearrange this, what we get is that n equals L over alpha plus beta Y, which if you divide, if you factor out the L, if you like, if you substitute LC for Y, what you get is a 1 over alpha over L plus beta C. I mean, you notice here that N is declining in C, which kind of makes sense, right? If the consumption for each individual variety increases, here we have a fixed number of workers. If you want to consume more of each variety, where you have to move workers away from the fixed cost of production into the production of the variable part of the cost, and therefore you're going to reduce the number of varieties. So that is our closed economy model. If you want to know what happens to trade, stay tuned for the next lecture. So that's it for today. I'll see you next time. Thank you for watching. Ciao.